So for this lecture and the next lecture, I'm going to talk about how memory allocation is handled inside of the OS kernel. It turns out to be a very important thing to do effectively and do well, because any inefficiency in how the kernel manages memory will affect everyone in the operating system's universe. So that's important. And then the other aspect of it is that the kernel is the longest running piece of software on the computer. If you think about it, the kernel's there when the computer boots and it runs, and then it's there right before the computer shuts down. So any inefficiencies in how the kernel manages memory are going to compound and multiply in a number of dimensions. And so it's very important to make sure that we get this problem solved correctly. So we have a lot of data structures that kernels have. Now, you've already seen a few of these things, like your thread structs and various lists and so forth, and you've already seen the intrusive linked list approach and mechanism, which allows you to avoid allocations if you have things that need to be allocated anyway, and you want to string them together in various ways. It's really easy through intrusive linked lists to manage such things. So that's nice, but there's still, smaller than a virtual memory page objects that we need to allocate and deallocate from time to time. A great example, and I remember talking to a student about this last time, is the thing that tracks a process's exit status, because the parent and the child need to be able to communicate with each other about that. So that's a great example of something that needs allocated, and a proper operating system kernel will have a pool of these things that it needs to manage. Okay, there's also buffers that we need if I'm going to send and receive data on a network, or if I'm going to interact with the disk controller, then invariably I'm going to need buffers of certain sizes to interact with those peripherals. It's inescapable. So the kernel needs some kind of dynamic memory allocation mechanism that will satisfy these requests. And there's two kinds of allocation that occur inside the kernel. You may have already noticed this in Pintos's implementation. You have what in Pintos is called pallic, which is allocating pages from the virtual memory system. Basically what we're doing is we're adding a page. It's actually called a page frame. That's the terminology that we use. It's a physical page of memory that we map into the virtual address space of something running in the OS. And so we're giving chunks of memory from the physical memory system to a process or to the kernel. Okay, so that's called page allocation. We're going to talk about that a lot more in the future. And then we may also need to allocate a chunk of memory to do something inside the kernel. And I have a few examples here. And so the second thing is what we're going to talk about today. That's the kernel memory allocator that handles those kinds of allocation requests. You can imagine it may need to interact with the page allocator, but typically we stick to just discussing kernel memory chunks being allocated in this in the next lecture. Okay, there are a lot of parts of the kernel that use the allocator. We've already talked about that, so it must be fast. And it actually has another challenging constraint, which is that sometimes the kernel allocator will be called from interrupt context as well as from process context. And remember, if I do anything in interrupt context, it has to be able to progress. It can't block passively, because I must execute and complete the interrupt handling, preferably as fast as possible. So I need to get it done. I need to get back to whatever I was doing before for the sake of latency inside the kernel as far as responding to events. So if I am in interrupt context and I get a call to the kernel allocator, I can't passively wait. And so this particularly becomes an issue when the OS kernel is in a low memory state. And we have a very straightforward way of handling this. When we're in process context, we just find a virtual memory page that it hasn't been used very frequently or very recently. It depends on our strategy. And we take the page frame away from that virtual memory page, which means we save the content somewhere else, and then we assign that frame to some other virtual memory address range so that we can now use it for something else. And in this case, it would be for a memory allocation. Now, the problem is when we evict a page back to disk or whatever swap device we have, and then we load whatever we need to set up the page table mapping, that will take hundreds of thousands of clocks, possibly millions of clocks, and we cannot do that in interrupt context. We must not block the executing interrupt handler. Okay, so we tend to have two modes for kernel allocation. We either have, I'm allocating an interrupt context, and you must finish whether or not it's successful or failing, and it's certainly possible in this context for a failure to occur. The way that OSs deal with this is they will have a special pool for interrupt handlers that is guaranteed to be available. And so that's the way that the kernel avoids having to pause or block passively, and also avoids failing the allocation request, because that may be a serious problem. And then if you have an allocation request in process context, who cares if it takes a while, if it dramatically increases the likelihood for success. So in that case, you can page fault, you can evict a page and take a frame and put it into another virtual address space and use it for an allocation request. So hopefully you see that kernel allocators have quite a challenge to solve here. Now, I was mentioning that there are a number of dimensions on which we need to be efficient if we're talking about a kernel allocator. Memory usage is one of the biggest ones. The kernel's running for a very long time, hopefully, if we don't have a sucky kernel, and we don't want to impose a resource allocation overhead on the OS, because then that's memory that applications can't use. There's also this issue of fragmentation, and fragmentation is actually a very serious problem within the kernel and requires careful management or careful strategies to be chosen to ensure that fragmentation is kept at a minimum. So there's two kinds of fragmentation that can occur, and this is from the perspective of the allocator itself. So is it external to the allocator or is it internal to the allocator? That's the easy way of keeping these distinctions in mind. Is external fragmentation is due to the behavior of programs making allocation requests. So you get allocated in free blocks that become interspersed, and perhaps especially in a language like C or C++, you can have pointers into the middle of blocks. You can have blocks pointing to blocks, and so that makes it so that you can't just slide blocks around. You can't coalesce the free memory to one region, because that would mangle data structures. And so external fragmentation is a very serious issue. So you have this example allocating blocks of various sizes. So you allocate 1 kilobyte, then you allocate 2 kilobytes, you allocate another 1 kilobyte block, and then a 2 kilobyte block, and then you free the 1 kilobyte blocks. Now you can see, because this is simple, that there is 2 kilobytes total available in the memory pool, but we will fail any allocation request that is above 1 kilobyte, even though there's 2 kilobytes available. And this is because of memory fragmentation. Okay, specifically external fragmentation. This is the behavior of the program making requests, or the order in which the requests come in, interacting with the allocation strategy that the allocator implements. So that's one issue. Another issue is internal fragmentation, which may be due to the way the allocator manages the memory pool. So internal fragmentation is fragmentation just due to the design of the allocator. So let's say that the allocator only hands out memory blocks that are multiples of a kilobyte. And so if we had these allocation requests, 750 bytes, you can see the red section is a little bit of waste. 1800 bytes, we have a little bit of waste. 690 bytes, we keep rounding up to the next kilobyte. And then 1320 kilobytes, which is a terrible allocation request. And you can see that we've already lost almost 1.5 kilobytes of memory just to the fact that our allocator only allocates multiples of 1 kilobyte. So that's internal fragmentation. Now I see that there is a A question, why can't you just coalesce in that case? So this is a very interesting question. If you're talking about a language like C or C++, where it's possible to do pointer arithmetic and to have pointers into the middle of structs, I want you to think about your intrusive linked lists where each element or each node in the list is a pointer to the next pointer in the struct. It's not a pointer to the start of the struct, it's a pointer into the struct. And think about what would happen if you just slid all of those in memory together. You'd have to be able to track down all the pointers and make sure they're updated properly. And this just becomes prohibitive, particularly if you're managing allocations in a language like C or C++. Now, if you're talking about a language like Java, and Java is an example where you don't, nobody writes an OS kernel in Java, at least I hope not. I think that people used to consider this back in the 90s, but nobody does consider it any longer. Java has an opaque reference type, which means no pointer arithmetic. You're not allowed to access the value of the reference or what it referenced. I mean, you can access what it references, but you don't get to know the address of it. That gives the virtual machine the ability to move the location of objects because you have a level of indirection between the code accessing the object and the object itself. And so because of that, it does allow you to coalesce. So garbage collecting allocators coalesce free memory into pools so that it can avoid the issue of external fragmentation. And it's hugely effective. Now, you might say, why is he talking about this? Java, nobody writes operating systems in Java. Well, it turns out that older operating systems would be able to hand out references of some kind to objects. Windows is a great example of this. If any of you are familiar with Windows API programming, you'll notice that everything is represented by a handle. And there's a reason for this, because that allows the OS to have a level of indirection between the thing it gives to the user or the caller of the APIs and the object itself, so that the OS kernel can coalesce memory and keep pools, or keep pools as large as possible. So using some kind of indirection like that within the kernel is what would allow you to implement coalescing inside the kernel. So it's a great observation and a great question. And older operating systems would do this like crazy. Now, what I want to just sort of give you a tease for the next lecture that we'll have on Monday is that we have other strategies now, like what Mac OS uses and what Linux uses that are very powerful. And it turns out that we don't need to coalesce as much with those because we're clever in other ways. And so while coalescing is very common in virtual machine implementations, it's actually not particularly common in modern operating system kernels any longer. So great question. It's easy to get sidetracked about this stuff because it's super interesting. Okay, let's see. So the kernel needs to increase its available memory size. So it will ask the virtual memory subsystem for page frames. This is what I was mentioning before. I know I'm introducing terminology before we get to it. We'll talk a lot more about it in a few weeks. But IA32 as an example has virtual memory pages that are 4 kilobytes in size. When I say 4 KIB, technically people say kibibytes, and that means kilo binary bytes, which is just ridiculous, but it just means 4096 bytes. So that's 2 to the 12, I think, as opposed to 4000, 4 with 3 zeros after it. So this is a common scenario. Allocator tries to satisfy a request from currently available memory in the virtual address space. So there's page frames behind the virtual addresses, so it can use that memory to make allocation requests. And it can't find sufficient space. So it has to turn around to the page allocator and say, hey, I need 1 or more new page frames, and I need to put them into this virtual address range so that I have more memory in my pool. So that's basically what's going on there. We want to maximize the use of these virtual pages. And you'll notice that if it's a certain size, always 4 kilobytes, then it would kind of make sense to design the allocator to work efficiently with that page size all the time. So as I have here on the slide, a good kernel allocator will take the virtual memory system into account. It will somehow be able to work efficiently and effectively within the constraints of the page allocation system. So you can start to see the constraints that the kernel allocator has to satisfy. Now, one of the things I love about Adam's new CS24, and I realize this may elicit more tears than we've already seen in chat, but the old CS24 memory allocator was actually simpler. The requirements were simpler than the current CS24 memory allocator. But the current allocator is much more realistic. So I'm glad that you get to see some of these things. As we go through the discussion this time and next time, you will recognize some of the things that are done, but then there's another level of requirement or another level of capability because you're in the kernel and you need to handle these things. I'll also mention, just for the sake of any tears, that the old CS24 allocator only had 1 week to complete it, and now we have 2 weeks to complete the newer, more sophisticated allocator. So I think overall it's a great improvement, even if, I mean, it's always a difficult problem for students, because when you have just a sea of bytes and you have to impose order on it, it's a challenging new problem. Most programmers aren't used to it because we are used to living in a very organized world. And file system data structures and memory allocators are both examples where that's challenging. Same thing with compilers. Okay. Yeah, so the allocation patterns within a kernel are actually well studied and well understood, because if you understand them, then you can design an allocator that works well in that kind of environment. So you can actually design the allocator to work efficiently with the allocation request. And that's why I was mentioning, when we talk about the allocators next time, they're designed the way that they are because we understand how kernels typically manage and require memory. Allocation requests tend to be bounded by some upper size, and it tends to be for larger I/O buffers used by peripherals, whether it be disk controllers, whether it's transferring data to GPUs, whether it's pushing data across a network, whatever it is. These large requests tend to be infrequent, and they tend to be bounded in size. They also tend to be a multiple of the virtual memory page size, because the peripheral probably is also aware of the page size, because peripherals are obviously built for specific platforms and processors. Now, it is also common to have many requests for a specific size. You've got a bajillion processes being constructed and, forked and then terminating. You've got files being opened and closed, so you need to allocate your file structs, or you need to keep track of the offset in the current file that a process has opened. So you have a lot of allocation requests for a particular size. Also, processes live, they work, they die, they're reclaimed, and then more processes come in their place. And so you end up with an allocate free, reallocate type usage pattern, which means if you can design the kernel allocator to do some kind of object pooling, hint, hint, that's what we're going to talk about next time, then you can make an extremely efficient allocator that dramatically minimizes the specters of internal and external fragmentation. So taking all these patterns into account can lead to a very efficient and effective allocator. Okay. Let's see, simplest kind of allocator you've probably heard called an explicit free list allocator. I suppose even simpler than that would be an implicit free list allocator, but explicit free list allocators tend to be far more efficient when it comes to satisfying allocation requests. So why would we have an implicit free list allocator if we can do explicit? So in the context of operating system kernels, you'll also see it called a resource map allocator or a sequential fits allocator. And so you can think of it as maintaining a list of free regions in the memory pool where it's just starting address, size of the available block. Now, we sort of describe this as a separate list, kept separate from the blocks, but as you probably remember from CS24, we tend to do this by stringing the blocks themselves together. So we actually store the pointer to the next block in a free block, and we also store the size of the free block in the free block so that we don't lose a bunch of space to it. Remember, this is nice. This is a way of the kernel allocator reducing its memory overhead. And if you have a pointer and a size and you're on 32 bits, that's probably 8 bytes total. So a minimum allocation size of 8 bytes is super nice, because a lot of times, if you need to support a long or a double in a allocation, then that's great. I think on modern 64-bit operating systems, you'll see a minimum allocation size of 16 bytes, maybe even 32 bytes. It depends on how the allocator is written. Okay. If the list is maintained in order of increasing base address. So think about, I've got these blocks and they are linked together sequentially. Well, that makes it really easy to tell if, when I'm freeing a block, if the next block is also free, because if it is, then I'll just combine them and make a larger block. It's a little bit more challenging if I free a block and the previous block is free, but there are techniques of implementing that highly efficiently, typically maintaining a header and a footer on every block, where the header and the footer are identical. Because then if you have the header of one block, you just subtract the header size from that pointer, you get to the footer, and then you're like, oh, you're also free, great, and then you just coalesce them together. So increasing base address makes it nice and simple for coalescing free regions, but the problem that you have is if you want to do a best fit allocation strategy, you kind of have to hunt through the entire list. So another option is maintaining the list in order of increasing size value, because then it's very easy to look for a block that is just barely large enough to hold the request that you're looking for. And so you see that the benefits are easy to implement, very little internal fragmentation, because we're fitting allocation requests as best as we can. Typically, you'll use a first fit or a best fit strategy, and they tend to work very well. And so you have various, techniques you can use here, and it's simple. It's easy to build. Now, the drawback is that you are now susceptible to whatever the other code that uses the allocator does as far as sequence of allocation requests, and this particularly increases over time, and the kernel is the longest running thing. And so you have to be really careful about managing external fragmentation in these kinds of situations. You end up with a bunch of little allocated blocks interspersed with a bunch of free blocks, and you're stuck. You have to figure out somehow. You have to have a strategy for working around that. Okay. Also, this allocator is slow. Even with first fit, you're still going to be hunting through a list. So you have some kind of order n time complexity in your allocation requests. And freeing may be constant time. You hope that it's constant time if you do it right, but allocation can be order n allocation. Okay, let's see. Yeah, and you can see the resource map allocator doesn't take virtual memory into account at all. So it's like, well, that's not very useful. We would very much prefer to have an allocator that does know about virtual memory, so that we can, because that's going to impose some external fragmentation. I'm sorry, internal fragmentation. See, I got it wrong. But it'll impose some internal fragmentation, because you always are going to get memory in a certain chunk size from the virtual memory system. And you'd like your resource map allocator, or whatever allocator you have, to be aware of that. Okay, power of two free list allocators. This is also something you're probably familiar with from CS124, often called segregated free lists or segregated fits allocators, because you have a number of allocation sizes and you tend to maintain a free list for each allocation size, so that it's easy to know generally what blocks will be available to satisfy an allocation request, or if there are no blocks, what do you need to do to resolve that issue? Okay, so as I say here, if a request spans multiple virtual pages, you may round it up to a whole number of virtual pages. If you have a request for 58 bytes, that would be stored in a block of 64 bytes. So you're going to lose. So this is internal fragmentation, because you have a rule. You don't hand out 58 bytes. You only hand out powers of 2 block sizes. So you lose some space due to internal structural approaches of the allocator. Okay, so you have an array of free lists, like I was saying. Each one is for a different size. And so you know that the blocks in those free lists are that size when you're trying to satisfy allocation requests. Okay, so this is going to be fast. In fact, it's going to be super fast. Most of the time, it's going to be constant time, because let's say that we have an allocation request of 200 bytes. So the allocator rounds that to the block size that will work for it, and it says, oh, there are definitely blocks in the 256 byte block list, and it can pull the first one off of that list in constant time. So allocation requests are very efficient. Cool. The challenge is when you're freeing. Like it says here, freeing is fast because you just need to figure out what free list corresponds to the block and stuff that block back into the free list. And putting a block into a list is also fast because you just stick it on the front, constant time. The challenge is you have to figure out what list does a block go into, because all you have is a pointer. And maybe you have a little header or something like that so that you can remember some information about the block, but you're kind of stuck. This is a big problem that Power of Two free list allocators have to solve. So what you can do is just say, well, we'll just devote a little bit of this block to remembering where it came from. So as I have on the slide, maybe it's a word that points back to the free list. Maybe it's a value that says, you know, this is the power that 2 is raised to for the block. So like for 256, that would be 8, if I can do math correctly. You would just store an 8 in there or something like that to say, yeah, this is a block that's of size 2 to the 8. That seems reasonable. But the only problem is that both programmers and hardware really prefer Power of Two block sizes. And so if you have Power of Two block size requests coming in, well, that will not fit because you're losing a bit of your block. And so it ends up requiring the block size to be doubled, because if you want a 256 byte block, well, the 256 byte block doesn't have that amount of space because you have to have a little bit of space devoted to bookkeeping. And this happens a lot, and a lot of space is lost when you have a Power of Two free list allocator that behaves this way. Okay? So if you have a situation, for example, where you have a request for a 64 byte block, well, it's pretty easy to handle this, because what the allocator can do is simply go up the allocations in block sizes until it finds one that's large enough, and then it can just split it. And so you can take a larger block and split it repeatedly into as many small blocks as you need. So in this case, we have a 64 byte request, or I should say a request that is satisfied by a 64 byte block. And so we take a 256 byte block, we split it into two 128 byte blocks, and then we take one of those and split it into two 64 byte blocks. So we could do something like that. Now, this also becomes a challenge because when we start splitting these large blocks, it's now harder to coalesce. Maybe you can solve that problem again with the header footer type solution, but now you're losing more space in your Power of Two size blocks, and so that'll exacerbate memory issues when it comes to trying to deal with this scourge of Power of Two allocation requests, things like that. So coalescing becomes more of a challenge with this kind of approach. Also, you'd like to think about virtual memory. If you need to reclaim a virtual memory page frame, you'd like to make sure nobody's using it, and therefore you need to somehow tell that all the blocks in the frame are in free lists. And that becomes harder to do when you split and merge blocks. So this kind of stuff just makes it a lot harder from the bookkeeping perspective. Okay, benefits: very fast allocation deallocation, good at reusing previous allocations of the same size. Remember that allocate, free, reallocate pattern. Resilient against external fragmentation, because Power of Two size blocks pack easily, so we like that. But we do have big issues with internal fragmentation, because most of the time we can't use the whole Power of Two size block. If we're going to get all these benefits, we have to devote some of it to bookkeeping. And so you can see here that in one study, 28% of the memory was lost to these kinds of bookkeeping and sizing issues. Okay. So let's see. Yeah, and coalescing and page reclamation are hard to do without extra overhead, and that overhead then exacerbates this issue that we have of internal fragmentation. Okay, so that's power of two free lists. Another thing we can do, and this leads into the next allocation strategy, is to say, well, when we need more memory of a certain block size, why don't we just get a new virtual page and split the entire page into blocks of that size? So now we're starting to say we're going to take the pages into account. So we'll split the page into a number of blocks, all the same size. And that allows us to manage block sizes on the page level as opposed to on the individual block level. And this allows us to achieve some efficiencies of scale. So a 48-byte request, we get a new 4 kilobyte page, split it into 64 64-byte blocks. All of them go into the 64-byte free list, and then it becomes simpler. So you can see here we have no blocks of 64 bytes, so we get a page, and we just plop down 64 blocks of that size. And now we can actually manage the allocation sizes at a page level as opposed to at a block level. Okay, so this is called the McKusick-Carroll's allocator. And you may have noticed McKusick's name in the 4.4 BSD scheduler discussion in Pintos, because McKusick played a significant role in the design of BSD. But the McKusick-Carroll's allocator is a power of two allocator that uses entire virtual memory pages to have blocks of certain sizes. The blocks are powers of two, the pages are powers of two, packs great, and you have a limited number of virtual memory pages, so it's easy to maintain that information at a page level as opposed to at a block level. So yeah, you no longer lose this word to the block size in the allocated block. So that means that programs or code that's using allocated blocks gets to use the full power of two block size that they request. And so we have this array of details. 4.3 BSD would call this KMEM sizes. This was an external array with one element per virtual memory page that records, is it free? Is it allocated? If it is, what's the block size? And then there was one additional detail stored as well. Okay, block size or free, or this is a multi-page allocation. So this allocation is a continuation from a previous virtual memory page. So this might be the way that it is. You have a 1 kilobyte allocation, so that takes an entire virtual page. In this example, the platform had 1 kilobyte or 1 gigabyte pages. So a 1 kilobyte allocation would take an entire page. A 256 byte allocation would allow 4 allocations in a page. 128 byte allocations would allow 8 allocations in a page. And then you can see that there are, this is a free block. This is also a free block. This is a 3 kilobyte allocation. So we have 3 pages in KMEM sizes indicating that. This is clever. Okay, so when you need to figure out what a block's size is, let's say somebody's handing you back a pointer and saying, I don't need this anymore, you need to figure out the size of the block that that pointer pointed to. So you just take the address and divide it by the page size, and that tells you the index in this array that will tell you the block size. Okay, so address divided by page size. Now, if you want to get really specific, like if you were building this, it would be address minus the start of this pool, right? You have to do that because your array is going to be indexed from 0. So address minus pool start, that quantity divided by page size will give you the block size. Okay, so if we had a block address of 7424 and our page size was 1024, well, that would be divided by 7, or the result would be 7. What am I trying to say here? And you go look in there and the block size would be 128. Okay, now this idea of having a separate array describing the allocations in these virtual memory pages is a great like enabler, because you can extend this with how many blocks are actually allocated in the page. And you bump that number up on allocations and you bump it down on frees. And if that number is 0, you know you can release the entire page back to the virtual memory pool. So you can start doing other things with this kind of approach. This is a great approach, and it starts to incorporate awareness of the virtual memory system, and that's part of what gives it its great power. Okay? All right. Let's see, what else do we have to say here? Yeah, better than the simple power of 2 allocator, not great. Why is it not great? Well, because we still have a lot of internal fragmentation due to the fact that we only hand out power of 2 size blocks, okay? So we do have a reduction at least, because we've factored out the block size and other details from the blocks themselves and maintaining it separately. But the fact that you're handing out power of 2 size blocks, I mean, there's a lot of stuff that's not going to be size power of 2 in the kernel, like the little file things that say where your file pointer is inside the file. That's just not going to be a power of 2. I mean, it might be 24 bytes. So now you're losing memory every time a process opens a file, and that sucks. Okay, so another approach is called binary buddy allocators. Buddy allocators are a great technique where you constrain what you can actually coalesce a particular block of memory with. You might remember from our sort of resource list allocation or segregated fits allocation, these kinds of strategies, that we can kind of coalesce with anything that's next to us. If it's virtually adjacent, and what I mean by that is like it's adjacent in the virtual address space, we can coalesce it. Cool. But if we constrain that, then we can start doing some other things that are actually significantly more efficient. Now, we still have the issue of internal fragmentation, but coalescing efficiency goes way up. And so this is the approach of buddy allocators. Binary buddy allocators are buddy allocators that work specifically with power of 2 block sizes. And you might tell from the fact that there are binary buddy allocators that there are also other kinds of allocators that fall into this buddy allocator family. And if you're curious, you can dig into it, because there's a lot of interesting options in how buddy allocation is done. But binary buddy allocation is very common in operating system kernels. Every block is a power of 2, but we also say that there's a size order associated with the block. The size order comes from the fact that we have a minimum allocation size, which is a power of 2, and the minimum allocation size is size order 0. Now, every time we go up in size order, we double the size of the block. So if the size order, well, I think I actually have an example here. Why try to explain the example, and I'll just show it to you. If your minimum block size is 32 bytes, 32 bytes is what is it? 2 to the 5? Can Donnie do math? I hope Donnie can do math. But 2 raised to the 5th power, well, 32 bytes will be size order 0. Size order 1 would be 64 bytes. Size order 2 would be 128 bytes, and so forth. And you can imagine that there is some maximum size order based on the overall pool size. Okay? And for each of these size orders, we maintain a free list. So when an allocation request comes in, we round up to the next power of 2, we figure out what size order that is, and we can just go straight to the free list for that size order and see if there are any free blocks available. So probably when you're looking at this and you're saying, this sounds a lot like binary segregated fits allocation, and you'd be right. But there's also a few additional constraints that make coalescing super fast. Okay, so the initial state of the pool is that it is one large free block. Now we're assuming that it's a power of 2 in size. And if it weren't a power of 2, you can definitely construct some set of blocks that will maximally fill that overall pool size. But let's just keep it simple and assume that the overall pool size is a power of 2 as well. Just simplifies the math. Okay? And so you'll notice in the first point that I say that gives you a maximum size order. If you have a minimum size order that's, like I have on the slide, 32 bytes, and that'll be order 0, and you have a pool size of 1 megabyte or 1 binary megabyte. So as I have here, it would be 2 to the 20 in this case, so 1048576 bytes. Then you can do the math and see that 15 would be your maximum size order. So in that case, you would have an array of 16 free lists, 1 for each size order. The order 0 blocks would be 32 bytes, and the order 1 blocks would be 64 bytes, and so forth. But initially, you just have one pointer in the size order 15 entry that points to the entire pool. Okay, when you have a block of a particular size order, you can split it, and when you split it in half, now since it's a power of 2, you get 2 blocks that are also power of 2 in size. That is a block of size order, previous order minus 1, okay? And the blocks that are split from the same parent block are called buddies. This is why we call it a buddy allocator, okay? And this is important because not all adjacent blocks of the same size are buddies. Only if they are cut from the same parent block are they actually buddies. So if you have a free block of a given size order I, you can coalesce it with its buddy if the buddy is also free and also of the same size order, okay? And then you get a new block that's size order I plus 1. Okay, you make an allocation request. Well, you figure out the power of 2 that can hold that allocation request. If it's below the order 0 size, you obviously round it up to the order 0 size. And then you just go ahead and look in the free list corresponding to that size order, and you satisfy the request if there's a block there. Easy peasy. Okay, now if you can't find a block of the appropriate size order, then you start hunting and you go through your free list until you find an available block of a size order. It'll be much larger than what you need, but now you can start recursively splitting it, or let's say iteratively splitting it, because recursion is something you prefer to avoid in operating system kernels unless you have tail call optimization, which, well, now that I think about it, modern compilers are able to apply tail call optimizations even in C and C++. They couldn't do this trick when I was an undergrad, and it's pretty wild to me still to this day that you can write something like a factorial function that's recursive, and when you look at the generated assembly code, it's been tail call optimized. So that's pretty freaking amazing if you ask me. But anyway, if you have an available block of a certain size order and you need one of a much smaller size order, you just keep splitting it until you end up with an available block of the necessary size order. Easy peasy, okay? And you can say this is constant time because you have a fixed number of size orders. So, I mean, obviously, you can think of it as the time complexity is the number of size orders you have, but your memory pool size is fixed. So it's kind of limited in that way. Okay. Let me see. There's a question. Are the split blocks marked such that they know what their other half are? Or can they be coalesced with another free block of the same order? There's magic. That's the answer. And I'm going to show you the magic. I'm just so excited about it. It's just really cool. If you have a block, you can figure out its buddy just from its pointer. And so you just it's actually an exclusive OR. You can do an exclusive OR, and that gives you the pointer to the buddy. And then you can just go from there. So it's very nifty technique. I'll show it to you. Okay, order 0 block size is 32 bytes. Max order is 3, so that would be 64, 128, 256 bytes, or maybe it's a kilobyte. I don't know. You can do the math. So this is our initial memory pool state. We have one free order 3 block. We have a 20 byte allocation request come in. Of course, that is not, it would be 32 times 8. What's 32 times 8? I'm sorry, you guys happen to watch me do math here. I think it's 256 bytes. So 20 byte block, you round that up to 32 bytes, and you say, okay, that's an order 0 block, but we don't have any. So we need to split this order 3 block down until we have some order 0 blocks. Okay, so you split the order 3 block into 2 order 2 blocks. You split the left order 2 block into an order 1 block. You take the order 1 block, the left order 1 block, split it into an order 0 blocks, and now you have something to satisfy the request. Okay, and this is why you can actually build this iteratively instead of recursively, because you just keep picking the left block to split until you get a block of the appropriate size order. So that makes it pretty simple to implement. Okay, so this is our memory pool state. We allocate a 40-byte block. Remember, our order 0 size is 32 bytes, so we can't satisfy it with an order 0 block, but we have an order 1 block. So we go ahead and do that. Okay. If we allocate a 60-byte block, that is still order 1. So we need to split the right order 2 block, and we just go ahead and use the left order 1 block. So we end up with a pool like this. Okay, I'm going to go back to here, and you can see here that we have 3 allocations. We do have some internal fragmentation because we're only handing out blocks in sizes of powers of 2. Okay, that's the downside of buddy allocators and all of these binary allocation strategies. Now, they're used in specific scenarios. Like Linux actually uses a buddy allocator, but it doesn't manage bytes with the buddy allocator. It manages virtual memory pages with the buddy allocator. And the reason why is because it allows you to keep virtual address ranges that are contiguous or page frames that are physically contiguous very easily. And that actually becomes an important thing when you start talking about virtual addressing. So we'll talk about that more in the future. Okay, when you free a block, well, you mark the block as free, and so you start with that as your current block, and you say, hey, block, is your buddy also free and of the same size order? If it is, you coalesce them. Now you have a block of the next higher size order that's free, so you repeat. Find its buddy. Are you free in the same size order? Yes, then you create a bigger block. So you just keep doing this to coalesce up the memory tree. Okay, so you can only coalesce with its buddy, and so that does address part of the question in the chat. You can't just coalesce with any free block of the same size. You can only coalesce with your buddy, and it turns out that there's simple math you can do to find your buddy, which is why we have this constraint. Okay, so this is our memory pool state. Oh, look, we have one more allocation that came in. You can see the last order 1 block was also allocated. So if we free the first order 1 block, you'll notice that if we look at order 1's buddy, well, we'd end up looking right here in the buddy allocation pool. And well, it's not free and it's not the same size order. We can't coalesce. If we free the second order 1 block, well, this block, when you try to figure out its buddy, is to the right, not the left. And so we can't coalesce it either, because even though it's the same size order, the block isn't free. So we end up with a pool like this. You can see that there is some external fragmentation that occurs with this. So if we free the first order 0 block, now we have an interesting scenario, because this block's buddy is right here, and hey, it's also the same size order and also free. And so we can coalesce them into an order 1 block. Now we take this order 1 block we just freed, and we say, hey, who's your buddy? And we come over here, and hey, you're also order 1 and also free. So we go ahead and coalesce those blocks together. And so you end up with this pool layout, okay? Hopefully this makes sense to everybody, at least intuitively. Okay, we have this interesting characteristic that when you're looking at the offset from the start of the pool, it's important that this is the offset from the start of the pool. So if your pool doesn't start at a 0 address, then you have to subtract the pool start from it, from an offset with, or I should say a pointer within the pool to get to the offset, and then that's where the characteristic shows up. You can find a block's buddy by XORing the block's offset with the block's size. And what that'll do is toggle 1 bit either to a 1 or to a 0, and that happens to be the block's buddy. That's how this crazy thing works. So if you want to find the buddy of the second order 0 block, so you're right here at 96, and so there's the bit pattern for 96. The size is 32 bytes, so you can see that the 0, 1, 2, 3, 4, 5th bit is set if we're counting from 0. And so we flip that bit, and it gives us 64. So that's how we get from 96 to 64, and that's how we find the buddy. You can also look at these bits in the offsets from the start, and the bits, if it's 0, it means it's the left child or the left buddy, and if the bit is 1, it's the right buddy. So you can see that the bit pattern of the offset gives you the path down to a particular block. So it's interesting that you have these characteristics of the offsets within the buddy memory pool, which is what allows you to find these buddies efficiently. You can do it with a constant time calculation, okay? Add, subtract, some bit math, and so that'll usually be just a few CPU clocks if the values are already in registers, okay? So yeah, I'm not gonna go through this because we're out of time. Okay, but you can look at this. This is the clever thing about buddy allocators. Now, you do still need to keep track of the size orders for blocks and also whether the block is allocated or free. And the simple strategy for this is actually the same as McCusick-Carroll's. You just keep a separate array of the minimum resolution. So your size order 0 blocks, and you have entries in there that tell you the size order of the block that starts at that location. Okay, and you would get to it by taking the address and dividing it by the order 0 block size, and that would give you the index into the array. Okay, so that is how you can keep track of the size orders. You factor that information out and you maintain it in a separate array. So you can see that the binary buddy allocator has some overhead, but if your minimum allocation size is 32 bytes or commonly 64 bytes, then it's not too bad. You can actually have a pool that's pretty large without devoting a huge amount of memory to that kind of a information tracking. And like I said, Linux does this on the virtual memory page level. So you have a minimum allocation size of 4 kilobytes, and then you don't need a lot of entries in an array to keep track of that. Okay, I'm going to go ahead and skip the rest of this. I'll just give you the punchline. The issue with binary buddy allocators is in the context of allocate, free, reallocate. So a lot of times these things are written to defer coalescing because coalescing over and over and over again adds up. So a lot of times these things will defer coalescing to keep from incurring too much of a time overhead for coalescing. Okay, so that's the discussion for simple allocators. Next time, we're going to talk about other strategies that involve object pools, and you'll find that those are far more appealing, which is why they tend to be used most heavily in modern operating systems. Have a good Friday. Have a good weekend. We'll see you next time.